In our first 3 lessons, we covered many different shapes, and you learned how to find the area of several different polygons and gave you a lot of formulas. In this section, we're not going to look at any new shapes. You're not going to get any new formula to find. We're just going to consider the relationship between perimeters and areas of similar figures. So, not new shapes, but similar figures. If you recall, similar, when we use that word in geometry, meant that in 2 shapes, the angles were congruent and the sides were proportional. Not the same, not congruent, but proportional. We thought about this more commonly as the same shape, but different size. Same shape, different size. Those figures had congruent angles, and their sides were proportional. So, here's the relationship we're going to consider. When we talked about similar figures always had a scale factor. When we use this term scale factor, all we meant, very simple, was the ratio of 2 corresponding sides. It could be any 2 corresponding sides, doesn't matter which one. It was just the ratio of the sides between our 2 similar figures. So, let's say, in general, to talk about our relationship, the scale factor of 2 similar figures, we'll just call the ratio A to B. So, the length of one shape is A, the length of my larger shape or smaller shape is B. That's our scale factor. That's the ratio of the 2 corresponding sides. Well, if I were to find the perimeters of that same 2 similar figures and compare the perimeters, the ratio of their perimeters is going to be the exact same as the ratio of their sides. A over B, once again. And then if I were to find the areas of those 2 similar figures and compare their 2 areas in a ratio, because area is in 2 dimensions, the ratio of those areas would be A squared to B squared. That one side squared to my other side squared. That's the relationship between similar figures. Their scale factor and the ratio of their perimeters is the same. The ratio of their areas is those 2 values squared. Okay, let's get out of the abstract and work with a concrete example. So, take a look at these 2 trapezoids. The trapezoids at the right are similar. What's their scale factor? The scale factor is just the ratio of corresponding sides. We only have 2 sides labeled, so the scale factor is the ratio 6 to 9. 6 to 9. Always, 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 if you can reduce. 6 over 9, you can divide a 3 out of the top and bottom, is the same as 2 over 3. That's the scale factor, just the ratio of 2 sides. The ratio of their perimeters, even without knowing what the rest of these sides are, since I know the trapezoids are similar, the ratio, if I found the perimeter of the little guy and the perimeter of the big guy, would be 2 over 3. The same as my scale factor. The same as the ratio of the sides. Once again, without actually finding the areas of these 2 figures, since I know they're similar, the ratio of their areas is going to be 2 squared over 3 squared. The ratio of their sides, but just each squared, which is 2 squared is 4, 3 squared is 9. I know, without finding their areas, the ratio of their areas is 4 to 9. 4 to 9. Okay. How do we use that? If you flip to the back of that next page, it asks us the area of the smaller pentagon, here in this picture, is 27.5 centimeters squared. That's the area of this little guy. What is the best approximation for the area of the larger pentagon? And I think the most important piece of information missing from this line is that these two figures are similar. So I guess I'll have to add that. Forgot that. These two pentagons are similar. What's the approximation for the area of this larger pentagon? Just from knowing what the area of the smaller pentagon is. Well, the ratio of their sides is 4 to 10. If you can reduce it. It'll make life simpler. 2 over 5. And that makes the ratio of these two figures' areas. We'll say ratio of the areas 2 squared over 5 squared. Each of those measurements squared, which is 4 over 25. That's the ratio of these two figures' areas. I know the area of one. I want to find the area of the other. Let's set up a proportion, because we're talking about similar figures. So, the ratio of their areas, little pentagon is to big pentagon, 4 is to 5, as the actual areas, area of my little pentagon is 27.5. The area of my large pentagon is what I want to solve for. Let's call it A. We've set up a proportion. Talking about areas, we have little pentagon is to big pentagon, as little pentagon is to big pentagon. Once it's aligned, cross multiply to solve. So 25 times 27.5. That should give us 13, what would that be? 1375 is equal to 4 times A. And to solve for A, one step, divide each side by 4, and you should find the area is 171.875. It didn't tell us to round anywhere, so I'm just going to carry it all the way out. We were talking about centimeters, so centimeters squared. We used the ratio of their areas and knowing one area to find the area of the other figure. Let's try another example. Down here it says the scale factor of two similar parallelograms is 3 to 4. The area of the larger parallelogram is 96 inches squared. What's the area of the smaller parallelogram? So what it tells us is the scale factor between these two similar parallelograms is 3 to 4. That would make the ratio of their areas 3 squared over 4 squared, or 9 over 16. That's the ratio of their areas. I know what the area of the larger parallelogram is. Let's find the area of the smaller parallelogram. Once again, set up a proportion. Here's the ratio of the smaller parallelogram to the larger is equal to, I'm finding the area of the smaller parallelogram, and the larger parallelogram is 96 inches squared. So, talking about areas, we have smaller parallelogram is to larger parallelogram, as smaller parallelogram is to larger parallelogram. Just make sure you align those, and then once we have the proportion set up, cross multiply to solve. So 16 times A is equal to 9 times 96 gives you 864. One step, divide each side by 16, and you get A is equal to 54. We were talking about inches, so the area of the smaller parallelogram is inches squared. And don't forget common sense. So in this example, say I had flipped the A in 96. I had accidentally lined up the smaller parallelogram with the larger one's area, and I had solved for A. What it would do is give me some number in the hundreds somewhere. However, if I'm finding the area of the smaller parallelogram, and I'm saying its area is 100 something, that would be larger than the area of the larger parallelogram. That would not make sense. We should be getting a number smaller than 96 for sure, because we're finding the area of the smaller parallelogram. So that's a good way to double check at the end of your problem if you aligned these correctly. Okay, moving on to a more real-world case. So let's read it. During the summer, a group of high school students cultivated a plot of city land and harvested 13 bushels of vegetables that they donated to a food pantry. Next summer, the city will let them use a larger, similar plot of land. In the new plot, each dimension is 2.5 times the corresponding dimensions of the original plot. How many bushels can the students expect to harvest next year? So here's the idea. We had an original plot of land to harvest from, and we're going to have a new plot of land to harvest from. And the ratio of those two is 1 to 2.5. Right? We had our original plot. They said that the new plot, each dimension, so each side, is 2.5 times the dimensions of the original plot, which makes the ratio 1 to 2.5. We multiply the side by 2.5. This would make the ratio of our areas 1 squared over 2.5 squared. We're interested in the ratio of the areas because when you're harvesting some number of vegetables, that's in 2 dimensions, right? You have a garden and you have rows of whatever these vegetables are. Vegetable, 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 etc. Right? And if we increase each dimension by 2.5, we're multiplying this side by 2.5 and also this side by 2.5. We want to know how much area we're going to have to harvest next year. We're interested in the area. The ratio of their areas then is 1 squared is just 1. 2.5 squared is 6.25. So set up a proportion to see about how many bushels we can expect next year. Original plot of land is to new plot of land. As in the original harvest we got 13 bushels of vegetables. How many will we get in the new harvest? So we're talking about the area. Old or original is to new, as original is to new. Cross multiply to solve. 1 times b is just b, and 6.25 times 13 gives us 81.25 bushels. So if we harvested 13 bushels of vegetables and then they increased each of our dimensions by 2.5, right, you can imagine we made it bigger, by 2.5, in the new area, how many bushels could we harvest? About 81.25. Okay, last example we're going to look at uses the same concept but driving down the road in the other direction, as I always say. So in this case we're given two similar triangles. Instead of finding some area like we have in the last few examples, we are given the areas of the two triangles. And we want to know what is the scale factor. Well, if we use our original relationship that we wrote down, we said if the scale factor was, say, a over b, the ratio of areas would be a squared over b squared. So let's for a moment just say that this scale factor is a over b. If that's my scale factor, then the ratio of the areas of my two triangles should be a squared over b squared. Well, I know what the ratio of the areas is. The ratio of my areas is 50 to 98. That's what the two areas are, 50 to 98. Simplify if you can. Here's the ratio of my areas. You could divide the top and bottom both by 2 and get 25 over 49. So if this is the ratio of my areas, this is a squared over this is b squared. So if I want to know what a squared is 25. Take the square root of each side. I find that a is just 5 and b squared is 49. If I want to know what just b is, then take the square root of each side, and the square root of 49 is 7. So if that's the ratio of their areas, this ratio right here is a squared over b squared. So to solve for the scale factor, we're just taking the square root of each of these numbers to get back to a and b. And if the scale factor is 5 over 7, the ratio of their perimeters is the same as our scale factor, also 5 over 7.